And she's going to be talking about Tibanna, a cloud-based standalone workflow automation system for data processing at the 4D Nucleome Data Coordination and Integration Center. So, Soohyun, over to you.
Thank you very much for your introduction. Again, I'm Soohyun Lee, and I work as at the 4D&D CIC and Harvard Medical School, and I'll talk about the cloud-based automation system. So how do we run genomic pipelines on the cloud? That's the main theme, but I'll also talk about some context. So let's start with a pipeline. Usually if we have a pipeline, we feed it with the input data files and parameters, and then in the end we get the output. This is pretty universal. We can feed different input data files and parameters and get different output, and we can do it as many times as we want. And the more input files we have, the better, the more economic, because it takes a lot of effort, and usually it's a very time-consuming step to set up a pipeline. So once you set up a pipeline, you want to run maybe 10,000 data files. That would be great. It's a big investment to set up a pipeline. What if we want to set up 100 different pipelines, though? How are we going to do this? It almost never happens, and possibly because setting up one pipeline takes so much effort. And even if we do set up 100 different pipelines, and now your system suddenly changed. Maybe your HPC environment has changed from LSF to Slurm, and now you have to rewrite all the pipelines. And so it's not as efficient. It's not as worth the effort. So it's not a very good investment to create so many pipelines, and so it almost never happens in reality. But what if we have to do this? The best scenario would be make the pipeline as minimal as possible, take it out, and then create a common pipeline executor that can run various different pipelines. And then this pipeline executor can read a specific format that describes the pipeline, and then the pipeline itself can be fed as an input. So then with this pipeline executor, you'll be able to feed in different pipelines and different input and parameter, and then you get different output files. And what's even better is, in this case, you can simply change the pipeline executor without changing the pipelines themselves. So your 100 pipelines will be the same, and you change the pipeline executor, you'll be able to run the same set of pipelines on different platforms. Or you can even upgrade the pipeline executor so that it can run faster or more efficiently, add new functions, new features. So this is a more efficient way if you have to run 100 different pipelines. And to do this, you have to build a pipeline executor. You need this tool. And then the pipeline has to be written in a common format that can be read and parsed by the executor. And this kind of scenario is especially useful if you're running things on the cloud, because then your pipeline executor can handle all the cloud-specific tasks, and then you don't have to worry about putting those things into the pipeline. Some of the cloud-specific tasks could include transferring the file from a permanent storage on the cloud to the virtual machine on which you're going to run the pipeline. Transferring the output file from the virtual machine back to the permanent storage, such as S3. S3 here is a permanent storage of Amazon Cloud, for example. Your pipelines are unlikely to be on a virtual machine because you will launch a virtual machine when you need it, and then you will spin it down because you will pay for the amount of time that you're running the virtual machine. So it's unlikely that all of your pipelines are already on the virtual machine. So ideally, the pipeline executor will grab your pipeline from a repository outside the cloud, such as a GitHub repo, and then you bring the pipeline to the virtual machine and then run it. And what's even better is if this pipeline executor can also create the virtual machine that where all these things are happening. And if it can optimize a virtual machine, so that it can have right amount of CPU and memory and the storage that will be attached temporarily to the virtual machine. That will be even better. If it can terminate the virtual machine when the job is done, and if you can monitor everything, that would be great. So this is not new. It has been a lot of data commons and cloud-based web portals are using this kind of approach in general. There are many common formats for pipelines, including common workflow language and workflow description language. And there are packaging technologies. Such as Docker, which is also containerization technology, but if you have to install many dependencies to run a pipeline, packaging all into a single image and then later just generating a container would be a more efficient way if you have to bring the pipelines every time you run a virtual machine. So these technologies are all available, and what we are doing is to create this pipeline executor that meets our needs in a cloud-specific manner. And you might ask why we are worried about running 100 different pipelines. It's particularly important if you are working for a data coordination and integration center where you have to receive many different types of data from many different centers in your consortium or network and have to process everything uniformly. So let me just briefly introduce the Data Coordination and Integration Center at the 4D Nucleome. It's led by Peter Park at Harvard Medical School. There is an infrastructure team that handles most of the cloud-related things. It's led by Burak Alvar, and that's me. And then there are many researchers. And so 4D Nucleome is a program that was funded by the NIH, and it started in September 2015, aiming to understand the principles behind the three-dimensional organization of the nucleus in space and time, etc. It consists of 29 awards that can be categorized into 6 different initiatives, and then they were awarded to 24 distinct institutions. DCIC, or Data Coordination and Integration Center, is one of the 6 initiatives, and that's us. And so what does DCIC do? So we build a data portal. That's our main responsibility. And this data portal will contain all the data that comes from the other centers of the 4D Nucleome network. And we store the data, and we provide a mechanism for browsing and searching and visualizing this data for the public. And we also let people to query different and filter different data types. We also discuss with the rest of the 4D Nucleome network about the metadata standards, such as the details of the experimental protocols, and we also implement these metadata into our portal. We also discuss with the rest of the network about the file format standards and implement them. For instance, there is this pairs file format that we created that documents the pairs of genomic loci that we can use across the whole network. And then we build pipelines and we process the data. That's what we do at the DCIC. So my task mostly involves building pipelines and processing them and implementing some of the infrastructure components that can run these pipelines automatically on the cloud. So we're using the standard file pipeline formats, including common workflow language and Docker. So common workflow language is a very structured way of describing a workflow. It describes steps and inputs and outputs of steps, and the connection between the steps, such as which output of which step goes into which input of which steps. And it's either in JSON or YAML format. It's highly structured, and it's very computer friendly. if you want to develop any software tool around this, it's relatively easy. And we are using Docker to pre-install all the dependencies for our pipelines and then create an image so that the same set of dependencies in the software with the same versions can be used across all the data that we're processing. And we're sharing all these CWL and Docker images with the public so that anyone can use the same workflow to process their own data. So to do all this, we've created this workflow management system called Tibanna. We're running it on the Amazon Cloud or Amazon Web Service, mostly because our portal is based on the Amazon Web Service. We haven't expanded to other cloud services, but we're thinking about it. So it's based on a very simple set of building blocks. There's nothing really complicated about it. But we have been using this for the past year. We built a prototype about 2 years ago, and we've been actively using this for the past year and ran thousands of workflows and created thousands of processed files, and about 1,500 of them are already released after curation. And we are still using this, and also at the same time actively developing and improving the system. So it's based on the very simple and basic units such as S3 buckets, the permanent storage, and the EC2 instances, the virtual machines. Plus, we are using certain other components. For instance, we create an AMI, which is an image of a pre-configured EC2 instance that has a Docker engine and the CWL tools already installed so that we don't have to install every time. And when we launch an EC2 instance, we're launching it based on this image. And of course, there is a storage that we need to attach to the EC2 instance. For instance, if your data is 300 gigabytes, you need to be able to calculate what would be the input size, what would be the output size, how much intermediate files would be generated, and then you have to attach this to the EC2 instance so that you don't run out of space. But at the same time, you don't want to attach a very big EBS volume when you're running a very small file. So this is something that we have to control. And Lambda, we are using Lambda, which is a serverless code that we can launch immediately without having to launch virtual machines. And it has a runtime limit of 5 minutes. And we are using this Lambda to spin up and monitor the EC2 instances. And then we're using a step function, which is a step machine scheduler for these Lambdas. I'm going to go through a little more detail so that you have a better idea. So first of all, you will have your workflow on GitHub, and this CWL will be on GitHub, and the CWL will have the record of a Docker image that it's going to use, and the Docker image will be on Docker Hub. And your data input files are already S3. You can upload your input files there. Your output files will be also on S3 that you can download them later. And then in case of us, 4D and DCIC, we have the metadata that describes all the input files and output files and workflow runs and workflows at the data portal. So we also have to communicate with this part. So when you launch Tibanna, you first launch these step functions, which consists of 4 steps in this case. The first step function will launch a new Lambda function, which reads the metadata from the portal about the input files and creates a new metadata for the workflow run and process files. And then the first Lambda, after it's done its task, it will disappear, and then you will only pay for the amount of time that the Lambda was working. And then the second Lambda will spin up a machine that is pretty autonomous in a sense that it will grab the workflow and the input files and then run the workflow and create the output files and then constantly send a log file to the S3 bucket all on its own. And once you create this virtual machine, the Lambda function is done with its task, and so it can go away. And then the third Lambda function will regularly check the log files that was sent to the S3, and then wait for some time, maybe 5 minutes, and then check it again. So you can keep doing this until you are finally sure that it's done. And this virtual machine will self-terminate once all the job is done. And then this check task Lambda function will be able to check that everything is finished. And then the last step will update the metadata at the 4DN data portal to let us know that all the workflow runs are done successfully. If there was an error, we will update the metadata that there was an error so that we can run them again with the different parameters or after fixing the bug for the pipeline. So now all the components together. So this is basically the idea. It's a very simple way. So the idea behind this is basically we want to make the virtual machines as autonomous as possible so that we can minimize the upstream scheduler and regulator, and also make the scheduler as transient as possible so that we don't have to pay for instance, another virtual machine that works as a master node, because if we use Lambda functions, we will only pay for a very short amount of time. So this was the idea, and it's a cost-effective way, and we have been using this in production. So we also added a cost optimizer at the second step, which means when we launch EC2 instance, we can choose the right type of instance that has the right amount of CPU and the memory, and also attach the right size of the EBS volume, depending on the workflow and the data size and the parameters, such as the number of threads, for instance. And also, we wanted to make every workflow run independent and isolated from the rest of the workflow runs, which is somewhat distinct from a previous some other systems, so that we can optimize the cost for individual at an individual workflow run level. So that was the basic structure. And we also realized that the core part that does not require the 4DN metadata can be used by the general public. So we made this part available for everyone. And then Tibanna is an open source. The entire Tibanna is open source, and it's available on GitHub. And so thank you very much for your attention.
So it's a very interesting set of technologies you've got there. Can I invite comments, questions, thoughts, suggestions?
For the prediction of the workflows of the amount of storage and number of threads EC2 instance, what was the process to do that for all these pipelines? Was that fairly labor intensive, benchmarking and so forth, or what process did you use?
First of all, we have a Python function that can read another Python function. And so we have a Python function that can select the right type of instance based on different workflows and data input data size. And so basically, it's somewhat labor intensive in a sense that you have to create your own Python function for different workflows. But on the other hand, it is updatable. So what we do is we create a safe, rough, estimated Python function in the beginning. And then as we have better ideas, we adjust the Python function, the benchmarking function, so that we can further optimize the cost.
What happens if some of the workflow step fails? Can I restart it from that step, or I need to restart the whole pipeline?
That's a good question. So currently we're running the entire workflow on a single machine, and that workflow can consist of multiple steps, and maybe it can fail at one of the steps without finishing. Currently, we have no way of restarting but we allow the users to be able to SSH into the virtual machines anytime they want and check what's going on. And then, so we have a very, what should I say, convenient way of checking the results so that the failure won't happen again. But in the end, we'll have to run things from the beginning. So one thing we're doing is we divide the big workflow into multiple sub-workflows so that the failure of the second step doesn't require running a very intensive first step or something like that.
Can I ask one more question related to the answer you gave me? If I have two workflows, the first one produces indices, the second workflow uses those indices and maps some fast-view file to the reference genome. How do you bind the output of one workflow with the inputs of the second one? In a way that, for example, I don't need to run the first part of the workflow which produces indices each time I want to map fast-view file to the reference genome. I need to know that, okay, those results already exist in the system. How do you connect these two parts?
If we divide it into different sub-workflows, then the result output of the first workflow will be already on the S3. And in our case, it will be recorded as a part of the metadata in the 4DN portal. And so we will be able to, and we also know that this first step has succeeded because we can look at the logs. And so then after that, we can continue on the second step. And if they're running in the same virtual machine, the step dependencies are taken care of by the CWL tool, so CWL Executor that's running inside the virtual machine.